My name is Risto Kojcev, and today I would like to present you the work me and the AI team have been doing at Erle Robotics regarding exploring novel AI techniques for modular robotics. But before I start, I would like to present to you our AI team. So our AI team consists of 5 people currently, that we are focused on exploring novel techniques and applying them to modular robotics. We are a young and fast-growing team, and we look people to join us. So what is the problem we are trying to solve in the AI team at Erle Robotics? We have noticed that there are mainly 3 strategies for building robots. Most of you know the traditional way of building robots, where you first buy the component, then you have to integrate all of the components. And this is very hard and cumbersome process. For most of you know it probably already, and involves a lot of integration time, a lot of plugging together all the components, finding common interfaces, putting them together, and then finally, once you have all that ready, you can go and assemble your robot. And then, after a long time of integration, you can start programming the robot to have certain behavior. But what happens if something goes wrong? You have to go back, reintegrate all the components, and start over again. And once you finish all of this process, you need to test, adapt, and iterate all over again. So what we wanted to do is, at Erle Robotics, is wonder, can we make this process faster? Can we speed up the integration time? And the answer is yes. We can do that by integrating something called modular robotics, where the goal is to just buy the module, and since all these modules have a common interface, speak the same language, for example, ROS2 native language, you can go ahead and start programming, assemble the modules, and start putting time onto programming the robots to perform a certain task. And we have noticed that this process significantly speeds up the time when you want to build a robot. But another question we have asked ourselves is, can we go even further? Can we even speed up this even more? And we came up with a strategy where you have a modular robot that you can just buy the module, then you can define a task, then you can assemble the robot and let the robot do something called automatic training, which involves letting the robot perform a certain action, train it in simulation, and then see if it can achieve this goal, and go back and test it, adapt it, or retrain it if necessary. Then finally, once you have everything ready and the robot can perform this behavior, you can deploy it and ship it. But, however, this is easier said than done. So we have been working the last 2 years on a common infrastructure where you can see that involves a lot of components together. It involves defining a common language, such as the HRIM, which was presented by my colleague Irati yesterday on the lightning talk. And it involves a lot of hardware integration, a lot of system integration. But we at the AI team are focused on leveraging all the work that the rest of the team is doing and explore novel AI methods. We are working on different methods such as reinforcement learning. We are using or exploring proximal policy optimization. We explore trust region optimization, and we even go further and explore more complex methods such as hierarchical learning and imitation learning. While we were doing this, we have noticed that there are 2 unlinked worlds. One is the world of deep learning, AI, which really focuses on developing these methods, and we can see that recently there has been a boom into these methods. They have really advanced in computer vision, reinforcement learning, and many of them even have been applied to robotics. However, they usually use locked-in vendor simulators, and they're rarely applicable beyond research to anything real up till now. So we have wondered, can we take the roboticist tools that also are really leveraged today? They're really nicely developed, and many people use them, and even there is a conference for that, like this venue today, where everybody is speaking like open tools such as the ROS, ROS2, and Gazebo. And the answer is yes, we can do that actually. And what we put effort in is to create this common infrastructure that merges these worlds together, and we call that gym-gazebo. So now I want to dive a little bit into what is gym-gazebo and what you can do with it. So gym-gazebo consists of common infrastructure that combines together on one side, the reinforcement learning algorithm, and here you can have any reinforcement learning algorithm you want. Currently, we are supporting any TensorFlow, but I don't see a reason why you cannot add a PyTorch algorithm if you want. Then all of these reinforcement learning algorithms are combined into something we call the environment API, which combines the inputs and outputs of the reinforcement learning algorithm and translates them to ROS messages. And in this environment API, you can use all the tools of ROS you want. For example, we use the kinematics dynamics library, we use the URDFs, we use the common messaging system, and you can use either ROS or ROS2 into this environment API. Only thing you need, we have managed is to translate what is the reinforcement learning algorithm inputting and outputting to ROS messages. Thanks to that, we can also output the training into a gazebo simulator, and you can see how the robot is training, how the training is doing. If you have some error, you can go back. You can visualize everything very easily, and it's very easy to debug. What is cool about this is that it's completely open source. So here there is the link. Please check it out. And we have noticed that this package, which exists for a couple of years already, has gained a lot of community awareness, and there have been many projects that have been using it, some of them for educational, some of them in the research, and recently there are even companies interested in using it. But we at Erle Robotics are more interested into how we can apply the state-of-the-art reinforcement deep learning algorithms to modular robotics. So we have built different demonstrators that you can also see them in our stand. One of them is the modular articulated robot arm, and the other is the 3 or 4 degrees of freedom SCARA arm. And we have experimented with using these robots. However, while doing this, we have noticed that reinforcement learning takes a long, long time. That's a nice picture of me waiting for some results. And this is really cumbersome because, especially in the development time, when you need to see if something is working or not, you need to change parameters, train, wait. Okay, it doesn't work. I go back, I retrain, and so on. So we have wondered, can we launch multiple instances of gym-gazebo and run them in parallel, and by that speed up the training time? And actually, the question is, yes, we can actually do that. And this work that I would like to present you focuses on how we did that, and the goal is for me to give you the recipe. Unfortunately, we cannot open source it because it's very environment specific. You need to use a particular robot and to add it and to this platform. But I will give you some details how you can do that. So the workflow, it's pretty straightforward. It consists of a couple of steps. First of them is to orchestrate workers. This block calls multiple instances of workers, which are basically just a Docker container that you can call, that are called simultaneously. And when the orchestration of workers finishes, after the orchestration of workers, we initialize a global policy, which each of these workers feeds the global policy back as it simulates. So I will go into details into how we orchestrate workers and what is each worker. So to orchestrate workers, we leverage the Kubernetes cloud network, which is responsible for managing different Docker containers on the cloud. And it consists of something called replica, that each replica is a physical machine that can be either local or on the cloud. and it has its own resources. And depends on the resources that this machine has, you can either launch one or many Docker containers inside. And in the Docker container, which I will give more details what is, you can, depends on the resources of the machine, you can launch many Docker containers. Each of those Docker containers is fetched from a common place called Container Hub. And the VPN bridge server just manages where are these resources fetched. What is important to say that the Container Hub contains many Docker containers that inside are embedded a common API and all the libraries that you need to launch a gazebo simulation. So the worker basically is just a containerized version of gym-gazebo. It has all the properties that I explained before, and it contains all the necessary things to launch a gym-gazebo simulation specific to your robot. So you define the environment API here, where you say, I want to work with a 6 degrees of freedom robot. You have all the necessary things like the URDFs. You define which reinforcement learning algorithm you want to use, and you just launch multiple instances. Each of these instances generates something called rollouts, and it contains a local policy. So each of them is like launching normally gym-gazebo, and it has the same properties. It has a local policy depending on your reinforcement algorithm, and generates rollouts. And each of these are feedback to the global policy and are synchronized with the global policy. That way, we can speed up significantly the reinforcement learning training time. So we have performed 2 sets of evaluations. One is, as I said, on the 3 degrees of freedom SCARA robot, and we also repeated we launched also RoboGym onto the Mara robot. And here you can see two plots. One on the left, it's plotted how many iterations we need versus the mean reward. And on the right, we have plotted how much time you need to converge. For us, convergence is when we reach around 0, because in our environment, we have negative reward. You can construct your reward as you want. It depends on your robot. So we have noticed that when you launch one worker, which equals to launching 1 gazebo simulation locally on your machine, you need around 600 seconds to converge the network. Then if you launch that with 2 workers, you can speed up the time up to 400 seconds, which is around almost 7 minutes. And then if you launch 4 or 8 workers, you can go up. You can reduce the time to 300 seconds or 5 minutes. So we can see by doing this that there is a significant improvement, up to 50% of reducement of the training time when you use RoboGym. Another thing that we have wondered is, okay, how accurate, or what is the accuracy and repeatability of these methods? And while we were doing these experiments, we have also measured the accuracy and the reproducibility in simulated and in the real robot. We do all the training in the simulated environment, then we do a transfer learning and we'll just launch the neural network onto the real robot. So when we launch the neural network on the simulated environment, we have noticed that actually with 1 worker, you have higher inaccuracy compared to when you launch the network with 8 workers. So the accuracy with 1 worker is around 2.8 millimeters, while when you launch with 8 workers, the accuracy is up to 1.37 millimeter. The repeatability when launching with 1 worker is around 4.5 millimeters, and when launching with 8 workers, we have reduced that to 3.5 millimeters, so 1 millimeter better. How about the results in the real robot? Here we notice that they are higher. So when we launch the neural network on the real robot, we have accuracy up to 26 millimeters, And when we launch the same network with 8 workers, we have accuracy of 12 millimeters. Same, the results are also higher regarding the repeatability. Here we have around 29 millimeters of repeatability and around 10.8 millimeters when we launch the network with 8 workers. So this is due to something that we are working on. We are trying to improve that. It means that we still need to work on some aspects of the drivers and the transfer learning, but I think we're gonna manage to bridge this gap between simulated and a real environment. Regarding the Mara results, it's a pretty new robot that we recently released, so we only able to have the results with the simulated environment, and you can see they're really low regarding the accuracy. We came up with 0.05 and 0.08 millimeters, while the repeatability is equal and it's 0.2. How about the timing in this case? Here we have, since we are doing a point in 3D, so before that the SCARA point was in 2D, so you are trying to reach a point in 2D, while here you are trying to reach a point in 3D with orientation. That means you are optimizing for 6 parameters instead of 2. Therefore, the speed up is a little bit less. So we have noticed when you launch the simulation with 1 worker, you need around 3,000 seconds. You can see that it's already significantly, or 50 minutes. The time for converging the network is already 50 minutes for a more complex robots. And when we added additional workers, we managed to reduce this time up to 2,000 seconds, or that's around half an hour, which is 33% speed up compared to launching the simulation in one worker. So this is really motivating, and we are working on improving this, especially to have equal numbers into accuracy and repeatability. One of the things that we did is to explore a little bit complex methods. Here we have a video where we trained the robot in simulation, then we launched the neural network in the real robot. And here we did something a little bit different. We trained the robot with 1 neural network with 2 different configurations. We have a 3 degrees of freedom SCARA and 4 degrees of SCARA, and we set 2 targets for each of them. So basically the 3 degrees of SCARA is trained to reach 2 targets, the center of H and center dog. We repeated that with the 4 degrees of freedom, and all of this is trained in 1 neural network. Then we launch this neural network to evaluate on the real robot, and we can see that with the hierarchical learning, you can achieve, for example, the robot to have 2 different configurations, which proves that actually you can use this method and iteratively change the configuration of the robot, which is really motivating for us. Regarding gym-gazebo, we evaluated 2 different modular robots, and we achieved a speed up to 33% in the worst case for the 6 degrees of SCARA robot, and 50% for the SCARA robot, and 33% for the Mara robot. We ran this in 12 replicas in parallel, around 2 weeks of training time, and as you can see, the cost is really, really low, and spend like 214 euros for the whole training time. To conclude my talk, I would like you to show you some interesting things we noticed while we were exploring these neural networks. One of them was, can these networks be adaptable? So to investigate that, we plotted different tests when we launched the neural network on the real robot, and we plotted the trajectory. Here you can see the X and Y position, while the black circle is the target that the robot should reach, and we injected different levels of Gaussian noise into each joint. So we have noticed that, for example, if you insert Gaussian noise of 0.05 radians, which is around 2.8 degrees per joint, you can see that the neural network tries to adapt and even reach the target. And this is a neural network trained without noise, and on runtime, we inject noise each step of the time. What is more interesting is that even if we increase the noise, and we added noise of, with standard deviation of 0.1 radian, which equals around 5 degrees per joint, we can still see that the neural network tries to adapt. This is really motivating, and this really tells us that there is a promise into these techniques. Are they ready for production? I would say not yet, but thanks to the rapid and thanks to the infrastructure the community is building, thanks to the rapid development of many new methods, I believe that we can soon bridge this gap. This is quickly just all the details. We always publish our work publicly, so if you want to see some details about RoboGym, more implementation details, they're all publicly available. And thank you very much. Questions?
Thank you. Does anyone have questions?
Yeah, I tried it out, like, I think end of last year, but I really struggled to get it to work. Did you, like, was really something, like, did you some improvement on like how to install it and how to run it, and in the last year, and how long will it get it now to set it up for me?
We extended our readmes a little bit and explained more, and we also are updating from ourselves, but also there are also new updates from the community. So yes, so it's publicly available, so if you have any problem with the installation, just please post it on the issue. We can help you.
Okay. Well, thank you, Risto.
Thank you.